Hello, everyone. We'll be starting soon in a few minutes. I'm just going to give everyone a few more minutes just to hop on if folks are running late. All right, let's go and get started with our show for tonight. Hello, everyone, and welcome to our virtual planetarium show for tonight. My name is Abhimat Gautam. I'm a postdoc researcher here at UCLA, working with the UCLA Galactic Center group. I used to be a grad student, and I just recently graduated earlier this summer. And for tonight's show, I'll be talking about our Milky Way galaxy, the supermassive black hole at the center of the galaxy, and just kind of seeing what the galaxy looks like in the night sky. So that'll be what's on our agenda for tonight's show. Just to kind of start things off, I want to talk a little bit about what planetarium is. Even though tonight, unfortunately, we have to be virtual, if you were to come to one of our in-person shows at the UCLA Planetarium, what makes a planetarium really special is that it lets us see what the night sky would look like if you were to go outside to a dark, starry location at night and actually see what the night sky looks like. You can see the stars, different objects in the night sky. That's what a planetarium is. So here for our virtual show, we're going to try and recreate a little bit of that. And then we'll also talk about some of the cool science things that about the galaxy and the center of the galaxy that you can spot in the night sky, and then what astronomers and scientists are working on to better understand how our galaxy works and what are the different things in the center of the galaxy. So that's kind of going to be our show for tonight. So to kind of start things off, I want to first go into this application called Stellarium. So Stellarium is basically a virtual planetarium, and it's an application that you can download for free. It's available online. And on using the software, you can see what the night sky would look like if you were to go outside and go stargazing. So this is our software to help us see that. So what I have right now is the night sky at about 9 p.m. for tonight, as seen from Los Angeles. And one of the first things that I've done in this uh, um, to start things off in this view in Solarium is that I've kind of turned on the light pollution. It's sort of similar to what it might be in a big city like LA. And you'll kind of notice that you don't actually get to see too many stars, unfortunately, in a big city like LA. So one of the things that you'll kind of notice right away is like these sort of are the direction markers to help us see which way we're facing. And here is the sky, and here is just a virtual ground. And you see a few bright things in the night sky that even with the light pollution that can show up. Here are just some meteor showers that can be possible to show up, but a few bright things that you could see right away in the night sky are two of the really bright planets that are up right now. This is right over here is Saturn, and right over here, the brighter one is Jupiter. And you'll kind of see them up above sort of the southern part of the sky. And then you'll see a few other bright stars, but you don't actually get to see too much in the night sky because of light pollution. So light pollution is caused by particles in the atmosphere of our Earth. So this is usually a lot of water vapor, but in a big city like LA, you also get other forms of pollution, like smog that you might get out of cars and other industrial stuff, or what's especially big in the news right now from smoke from wildfires. And these particles in the atmosphere of our Earth end up reflecting back the light that's coming from the ground. And this light that's reflected back from these particles in the atmosphere of the Earth ends up overwhelming the light that's actually coming from outside of the Earth. So from the planets and the stars that we might want to see in the night sky. So that's why in a big city like LA, we unfortunately don't get to see too many things in the night sky because this light pollution, this light that's reflected back from the particles in our atmosphere, end up overwhelming the light that's coming from outside of the Earth. So fortunately for us, we can actually turn off the light pollution in Stellarium. So that's pretty nifty. So I'll go ahead and do that. I'll go ahead and turn down the light pollution. And this is to help us simulate what the night sky would look like if you were to go to a dark sky location away from the city. So here, I'll go ahead and do that. And as we turn down the light pollution, I'll move this window out of the way for a little bit. You can see that you can start to see many more stars in the night sky. And then let me turn this down all the way. And then you can start to see the night sky really well. You can see all sorts of stars in the night sky. And then there's this huge faint band of light that kind of pops up once we go to a dark enough location. And that's the Milky Way. That's our home galaxy. And that'll be the topic of our planetarium show for tonight. So just to kind of start things off, I want to actually pose a question to all of you. So our home galaxy is the Milky Way Galaxy. And we can see the Milky Way Galaxy if you're to go stargazing away from the city lights in a dark enough location. And you see this Milky Way as this sort of band of light that's kind of stretching all the way across the sky. It's a special, it's more easily visible during the summertime when we're looking out towards the brighter parts of the Milky Way. But you can kind of see this band of light if you go to a dark enough place stretching all the way across the sky. And you might wonder, why does the Milky Way look like that in the night sky? So that's actually a question that I want to pose to all of you. Do you have any ideas? Why do you think the Milky Way Galaxy looks like a band of light that's stretching all the way across the sky? I'll give you a few moments to kind of throw your ideas in the chat. And yeah, so I'd love to hear what you all think. What are some ideas why you all think the Milky Way looks like that in our night sky? Yeah, I'm already seeing some great answers. It is shaped like a pancake. Yeah, yeah, and we are in it. That's a great guess, like light reflecting off of the planets and the stars. That's a wonderful guess. We are spinning is another guess, and then we're inside the disk. Um, Dust clouds in space lit up by stars. Uh, Closer together they look like clouds. Earth rotates. Yeah, so these are all really great ideas and really great ideas of why the Milky Way kind of looks like the way it does in our night sky. So, kind of the answer is that the Milky Way is sort of like a disc-shaped galaxy. I love this answer that was given by one of our audience members that the Milky Way is sort of like a pancake. And that's actually a really great way to think about the Milky Way. The Milky Way is a thin, disc-shaped galaxy, and it's like a pancake. So pancake are thin disc-shaped objects, and the Milky Way is a thin disc-shaped object. So it's a pretty good analogy. So the way I like to think of it is, what if you were curious little chocolate chips inside of a chocolate chip pancake. And you wanted to know what the world outside of the pancake looked like. So, what do you think the world outside of the pancake would look like if you're a curious little chocolate chip inside of a chocolate chip? So, the world would kind of look something like exactly what we're seeing in the night sky. What we're seeing in the night sky is that the Milky Way is our pancake and we are the curious little chocolate chips. And the Milky Way pancake is kind of stretching all the way around us in this sort of thin little line that's our pancake. We're looking through into the pancake. And then we can also start to see above and below the pancake. That's us looking, we can start to see the world outside of the pancake as we start to look above and below the pancake. Some of these stars that, or actually all of these stars that we're seeing here, these are actually stars that are in the Milky Way. There's still some pancake stuff that's still around us as we're looking above and below the pancake. But all these sort of dark spots in the sky that you're seeing here, that's us looking outside of our pancake. That's us looking outside of our home galaxy, the Milky Way. And we can start to see the universe outside of the Milky Way. So pancake is a really great way to think of the Milky Way. So I want you to hold that picture in your mind as we kind of go through the show, that we're living inside a pancake. We're sort of like little chocolate chips inside a chocolate chip pancake. So let me switch over to my slides to kind of help us go on to our next topic. So, uh, so the Milky Way is this thin disk galaxy that's shaped like a pancake. And this picture that I'm showing you here is what the Milky Way would look like if we had a long selfie arm and we had a big camera that we could extend all the way above the Milky Way and take a picture of us from far above the Milky Way. That's what the Milky Way would look like. The Milky Way is a thin disk-shaped galaxy, and it's also a spiral galaxy, meaning it has these spiral arms. And these spiral arms are where there's a lot of stars and there's a lot of gas and dust. And these spiral arms make up the disk of the galaxy. And right over here, that's where we live. We live right next to our home star, which is called the sun. So you are all in that location in the Milky Way. And the Milky Way is this thin disk-shaped galaxy. So instead of us seeing something like this, because we live inside of the Milky Way, what we instead end up seeing is something like this. This is a thin disk-shaped galaxy. So because we're living inside of it, we end up seeing something like this. This is a panorama of the Milky Way, what the Milky Way kind of looks like. If you could take a panorama of the entire Milky Way across the entire night sky. So I've highlighted a few features, a few notable features that are interesting features of the Milky Way. So you kind of see that there's all this light that we're seeing here. This is pretty much all just individual stars. All of this light is pretty much all coming from starlights, stars giving off their light. And then we see these sort of like dust see these sort of like dark blackish bands that are obscuring the light. Those are called dust lanes. That's actually coming from dust that's in the plane of the Milky Way, and it's blocking the light of stars that are behind the clouds of dust in our Milky Way. So those are sort of some of the dust lane features that we're seeing in the Milky Way. And then over here, right over here in the center, our Milky Way kind of is a little fatter, it's a little thicker at the center, and it sort of bulges out. So there's this big kind of bulge of stars that's right here at the center, and then right over here is where it's sort of like the center of the galaxy is. So if we kind of go back to our previous picture, the bulge and the center of this galaxy, that's us sort of looking out at this part of our galaxy. We're kind of looking at this sort of thicker part of the galaxy when we're looking at that part of the sky. Okay, so if we actually kind of zoom in a little bit more, we see we can start to see the dust lanes much more prominently. So again, this is sort of like the thicker dust lanes that we're kind of seeing towards where the center bulge part of the galaxy is. And some people call this the Great Rift. It's basically just this sort of darker patch of sky that's being caused by dust clouds in our Milky Way. So this is the dust lane known as the Great Rift. And if you want to visualize where the dust clouds are that are kind of causing this, this dust lane. Uh, Most of this dust that we're seeing that's causing these dust lane that's known as the Great Rift, that's kind of located between us, where we are here at the sun, and sort of out towards where the bulge and the center of the galaxy is. So most of the dust is actually somewhere around this area. So that's where most of the dust is. So one of the things that I want you to notice and kind of keep in mind as we're looking through this is that these pictures are us seeing what the Milky Way looks like in visible wavelengths. So visible wavelengths are the wavelengths of light that our eyes see at, and there are actually other different forms of light as well that our eyes can't see at. But scientists have cameras and telescopes that can actually see at other wavelengths of light. So at visible wavelengths, meaning the wavelengths that our eyes can see at, what we end up seeing is that all the starlight ends up getting blocked by these thick clouds of dust. So these thick clouds of dust mean that we can't actually see very well what's happening uh, in different parts of the galaxy at wavelengths that our eyes see at, because these thick clouds of dust are in the way. So those are the dust lanes, and those are the dust lanes in the galaxy. So next, I actually kind of want to switch back to Stellarium for a bit, and let's try and see how we can find the center of the galaxy in the night sky if you were to go stargazing. So let me switch back to Stellarium over here. Okay, so again, we are at this time of the year at around 9 p.m. tonight, and this is what the night sky will look like if you were to go stargazing. So you can actually see the center of the galaxy if you're looking at the Milky Way during the summertime. And the way you can find the center of the galaxy during the summer is by looking for a constellation known as Sagittarius. So I'll help you see how to find the constellation Sagittarius in the sky. So here we are, we're looking towards the south part of the sky. So I'm here, I'm showing what the night sky would look like in Los Angeles. This is pretty true for the Northern Hemisphere overall. If you're further south of Los Angeles, things will be kind of shifted further up for you. If you're further north of Los Angeles, then things will be shifted further down for you. But here I'm showing what the night sky would look like around Los Angeles. So if you're around Los Angeles and you're looking at the night sky, you want to look for the constellation Sagittarius. And the way you can find the constellation Sagittarius is you can look for a group of stars that kind of looks like a big teapot in the sky. So let me help you see that. So here I'm going to turn on some lines to help us see some easy to see groups of stars in the night sky. And here we are, we're looking towards the south part of the sky, and this is the constellation Sagittarius. The entire constellation Sagittarius is much bigger, but we're kind of interested in this part of Sagittarius, which makes up a teapot. So let me just help your imagination here. So this is the pot part of the teapot, and then these four stars over here make up the handle, and then these three stars over here at the end of Sagittarius make up the spout. And it's really cool that in the night sky, the Milky Way is kind of going off from the teapot. It's sort of like steam coming off from the teapot, which is Sagittarius. So that's the constellation Sagittarius. And what's really, really cool about the constellation Sagittarius is that, and the teapot, is that if you find the teapot and you can find the spout of the teapot, you can follow the spout off a little bit, a little ways off. This is about 2 or 3 finger widths. If you hold out your hand and you're looking up at the sky, this distance will be about 2 or 3 finger widths away from where the tip of the spout is. And if you follow that out, you end up getting to where the center of the galaxy is in the night sky. So again, you find the constellation Sagittarius, you find the spout, you follow the spout out, and you get to the center of the galaxy here in the Milky Way. So the center of the galaxy is right over here. Let me show you how you can exactly find it in Stellarium. If you're looking for the center of the galaxy, you want to search for SGR-A star, standing for Sagittarius A star, and we'll talk a little bit more about that in just a bit, but that's where the center of the galaxy is. And boom, right there, you can find the center of the galaxy using Stellarium. So that's how you can find the center of the galaxy in the night sky. But unfortunately for us, because our eyes see at visible wavelengths, unfortunately, there's all these thick clouds of dust that actually block us from seeing what's happening at the center of the galaxy. So if we could zoom in, what you end up seeing is that there's a bunch of stars here, but where sort of the center of the galaxy is, you can't really see what's kind of going on because there's all this sort of dust that we saw that makes up the dust lanes blocking our view of what's happening at the center of the galaxy. So let me switch back to my slides. Um, Here we go. So here's again the picture of the entire Milky Way in the night sky. This is a huge panorama. So we can take this panorama and we can rotate it to something like what we would see if we're standing in the northern hemisphere with north sort of up towards the up, and then east towards the left of us as we're looking at in the sky if we were to go stargazing. And the way you find the center of the galaxy is you look for the constellation Sagittarius and you look for the group of stars here. Um, that's known as the teapot in Sagittarius. And then you follow the spout up the teapot, and right over there is the center of the galaxy. And we can see a close-up of the center of the galaxy in this picture. This is a much sharper picture of that region of the sky. And again, here's the teapot, and then here's the center of the galaxy in this dark part of the Milky Way in the night sky. That's one of the dust lanes in the night sky. And if you kind of do an even more close-up, you can kind of see like where the center of the galaxy is. You can kind of see some stars with your eye at visible wavelengths, but you can't really see exactly what's kind of going on there. And that's because of all the dust in our galaxy in our way that's blocking the light that our eyes see at. So that's kind of a bummer for us, but scientists are pretty clever, and scientists can actually can use instruments like different cameras and telescopes to see at other wavelengths besides just visible wavelengths. So uh, one of the convenient things is that if we look at wavelengths that are much longer than what our eyes see at, something like infrared or radio, we can actually start to see what's happening at the center of the galaxy because these wavelengths can actually travel through the clouds of dust towards us. So here we have an image of the center of the galaxy that's seen in near infrared wavelengths with the Hubble Space Telescope. And this is an image of the center of the galaxy that's about 4 parsecs on the side. And you can see it's basically just a whole lot of stars. Like there's a huge amount of stars at the center of the galaxy. And this huge cluster of stars is known as the nuclear star cluster. This is something we can't really see very well with our eyes, but in infrared, you can start to see this cluster of stars really well. So this is the nuclear star cluster that's being seen with near infrared wavelengths. So if we want to zoom in closer into this image, let's start off with this image. And this image is coming from the Hubble Space Telescope. We can start to zoom in closer towards the center, where the center of the galaxy is. And we start to do that with this image that's coming from Hubble, taken in near infrared. And what we end up seeing here is that it starts to get really, really blurry. At the very center, there's just so many stars that we can't actually see very well what's going on because there's just so many stars, it gets really, really crowded. And with a telescope like Hubble, we can't actually make out what's happening at the center, at the very center, because there's just so many stars. So that's another challenge if astronomers are trying to understand what's happening at the center of the galaxy. Telescopes like Hubble, even though Hubble is really great, they're not good enough to let us see what's happening at the center. And this is because of something in astronomy that astronomers take advantage of, is that bigger telescopes actually have something that's called a better resolution. So what we mean by when we say bigger telescopes can have better resolution is that a telescope with better resolution can take sharper images of smaller objects in the sky. So if we want to see what's exactly happening at the very center of the galaxy, we actually have to use telescopes that are even bigger than something like the Hubble Space Telescope. So the Hubble Space Telescope here that I'm showing here on the slide is actually really, really big on its own. It's actually not a very small telescope. So here's a picture of the whole telescope, and here's actually a close-up of the back end of the telescope when when astronomers were actually repairing it several years ago. And this is the space shuttle which the astronomers took to get to the Hubble Space Telescope. And here's the back end of the telescope. And you can actually see the entire telescope is kind of like the size of a person. And the way you can kind of measure the size of a telescope to judge how good resolution it has is you can measure the size of the primary mirror, meaning the biggest mirror in the telescope. And for the Hubble Space Telescope, this mirror is about 2.4 meters tall or about 8 feet tall. So it's about a little bit taller than a person. So here you can kind of see it next to an astronaut. There's the astronaut there, and you can kind of see that the Hubble Space Telescope is a little bit taller than a person. But it turns out we can actually build even bigger telescopes on the ground, telescopes that are even bigger than the Hubble Space Telescope. So on the ground, we can build much bigger telescopes. And one of the biggest telescopes that astronomers have built on the ground is a telescope known as the Keck Observatory. This is located on Mauna Kea in Hawaii. And this is actually an observatory consisting of two different twin telescopes. So both of these telescopes are sort of twin telescopes, and each of them has a primary mirror that's about 10 meters tall. So they're very big telescopes. They're among some of the biggest telescopes in the world. So kind of to compare what they are next to Hubble, let's go back to the slide that we had from before. This is the Hubble Space Telescope primary mirror. It's about 2.4 meters or about 8 feet tall. And then we can put that in context of the Keck Observatory mirrors. So here's the Hubble Space Telescope mirror again. There's a person, just for reference. That's how tall an adult person it usually is. So this Hubble Space Telescope primary mirror is slightly taller than them. And then the Keck telescope mirrors, each of them are about 10 meters across. That's about 11 yards across, or about bigger than 33 feet. So these are huge mirrors. They're much bigger than a person. And to kind of get an intuitive sense of how big these mirrors are and how big these telescopes are, we can kind of compare them to something that you might see more commonly every day. So this is a tennis court, and each of these primary mirrors of the Keck telescope are about half the size of a tennis court. So these are some of the biggest telescopes that astronomers have access to right on the Earth, and to look at the sky in near infrared. So if we actually go back to the picture that we had before of the center of the galaxy, here's what we were seeing with Hubble. At the very center, it's kind of blurry. There's so many stars that all start to blur together, and it's very difficult to kind of see what's going on. Hubble is really cool, but it can't really help us see what's going on at the center. And then if we switch over to a big telescope like the Keck Observatory in Hawaii, we can start to get a much sharper view of what's happening at the very center. And you can start to see that there's a whole lot of stars at the very center. So that's super cool. That's what astronomers use to help us get a really good sense of what's happening at the very center of the galaxy. What's happening with the stars at the very center of the galaxy in the cluster of stars known as the nuclear star cluster. And next, if we zoom in to the very center of this picture, right there, and we see what's going on. So this is a collection of images that have been taken by the Galactic Center group here at UCLA for over 25 years. What we see is that all the stars are kind of moving. And at the very center, we start to see that the stars are actually kind of going in these what looks like orbits around a sort of like hidden point at the very center of the image. And particularly if you notice this star, this particular star, we highlighted, it has a name called S02. It circles around this point in the sky. So here it is. Now we're tracing the orbit of the stars, and we can also see all these other stars kind of going in longer orbits that are span longer periods of time. And what that helps us see, so just to kind of get us, before we move on, just to kind of get a sense of scale of how big of a distance we're looking at, this movie is about the central 0.1 parsecs of the galaxy. That translates to about zero point 0.4 light years. So this is the central point for light years of our galaxy. And once we take this orbit that we're measuring for this star and other stars, what we end up seeing is that when we trace the orbits of the stars at the center of the galaxy, we find that there's a really, really massive object at the very center of the galaxy. So this is that same orbit that we were looking at in the previous slide. And by tracing the orbit of the star over many years, so this particular star has a 16-year orbit, we find that there's the center at the center, there's an object that's as massive as 4 million suns. And astrophysically, how the best way astronomers can understand an object like this is that it has to be what's called a supermassive black hole. It's a really, really massive black hole. So that's at the very center of the galaxy. So that's what we find at the center of the galaxy, and that's what astronomers can, that's how astronomers can know that there is a supermassive black hole at the center of the galaxy by tracking the motions of stars over a long time, and we can see that they're orbiting around an object that has this much mass. So just to kind of summarize this part of the presentation, here's what we could see at visible wavelengths in the night sky. You can find the center of the galaxy if you go outside stargazing. You can look for the constellation Sagittarius. You find the spout and you trace it out, and you find that there's this point in our galaxy. That's where the center of the galaxy is located. And at wavelengths of light that our eyes see at visible wavelengths, we can't really see what's happening at the center because there's a ton of dust that's blocking our view. Astronomers have to use instruments and telescopes that can see at other wavelengths of light, at longer wavelengths of light that can travel through the dust and let us see what's happening at the center. And when we do that, we end up seeing this image. This is an image of the nuclear star cluster as a whole. This is a big cluster of stars at the center of the galaxy. And if we want to peer it at the very center, we have to use the biggest telescopes on the ground. So using the Keck 10-meter telescope, for example, we can start to get a good idea of what's happening at the very center of the galaxy. So this is a picture of the central about 1.3 light years of our galaxy. And then if we look at the very center, we can see stars orbiting around a point. So this is looking now at the central 0.4 light years of our galaxy. And then by tracking those orbits, we see that there's a huge supermassive black hole at the very center of the galaxy. So that's how astronomers know that there is a supermassive black hole in their galaxy. So moving on from this, so we've been talking a lot about these black holes. And this is something you might have heard a lot about. And so far, I haven't really told you what they what are. So actually, I want to give you a few moments to kind of put down your guesses in the chat to ask about what black holes might be. What do you think are black holes? So just feel free to put down your guesses in the chat, and then we can use them to move on to the next part of the show. Okay, so I'm seeing a few great guesses. So burned out stars, pure materialized nothing. That's a really poetic way of saying what a black hole is. A really, really dark cold abyss where light cannot escape. Yeah, that's a really good way of putting it. Quicksand in the sky. That's a really great guess. I like that. The place all my missing socks go. Oh, I'm sorry. Sorry, all your socks have gone to black holes. Points of dense gravity, super compressed matter. I'll give you all a few more minutes or a few more moments to kind of put down your guesses. Hold stars that explode into a black hole. Wow, you all know a lot about black holes. Super compressed matter. Regions of space where gravity is strong and light can't escape. A virus in space. Unfortunately, no, not a virus in space. All right. So yeah, these are all really really great guesses. Yeah. So it's great that you all already know so much about black holes. So the way I like to think of it is that black holes are actually fairly sort of straightforward objects to kind of just describe. There's a whole lot of funky stuff that happens around them, but on their own, they're actually kind of straightforward objects. So in just like sort of a really really simple sentence. And we'll poke this apart, so don't worry if you don't understand the sentence quite yet completely. But black holes are objects that are so massive that you need to go faster than the speed of light to escape from them. And that's essentially what black holes are. We'll kind of poke apart this sentence in just a bit to kind of better understand this. So, so just to kind of start off with, one of the things that we're talking about is that what is this concept of escaping from something? What do we mean when we're saying that black holes are so massive that not even light can escape from it? So in order to kind of understand that, you have to understand this sort of like this concept from physics that's called escape velocity. And it's sort of this it kind of sounds complex. It's this sort of physicsy jargon word that you may not completely understand yet. But the basic idea is that all objects can have these things called this property called an escape velocity. So to kind of understand this, let's say you're on the Earth, like as we all are, and you're maybe trying to get off of the Earth. Maybe you just want to leave the Earth. What you might try first, you might just try jumping, and you'll jump, and it turns out you won't actually end up going very far. Eventually, you'll jump, and you might be able to get a few inches, maybe several inches off the ground, and then eventually the gravity of the Earth will catch up with you, and it'll pull you back down, and you'll come back down to the ground. So you won't be able to get very far on your own. And then let's say, well, if you want to get further, what if you built a rocket? So you built a rocket and you launch it, and maybe it doesn't go very far, and it doesn't go very fast. And eventually, it's not a very fast rocket, and you'll launch it, and it won't be able to get very far. Eventually, the gravity of the Earth will catch up with it, and eventually, it'll fall back down to the Earth. Maybe you can build a faster rocket and it can get even further, but eventually gravity of the Earth kind of catches up with it, and you can keep on building faster and faster rockets, and eventually they can get further and further, and at the ultimately you can reach what's called an escape velocity. So if you launch a rocket at this speed, what this means is that the rocket launched at this escape velocity speed will never return back to the Earth. So this is a phenomenon, or this is a concept from physics. So from the surface of the Earth, in order to build a rocket that would never come back to the Earth, you need to launch it at a speed greater than 40,000, about 40,000 kilometers per hour, or about 25,000 miles per hour. So that's the escape velocity from the surface of the Earth. So that's for the Earth. So for a black hole, what ends up happening is that for a black hole, the escape velocity of a black hole actually turns out to be faster than the speed of light. What that means is that if you want to completely escape from a black hole, you need to be going faster than the speed of light. And speed of light is about 300,000 kilometers per second, or about 186,000 miles per second. So just notice the units that I'm using here. It's not miles per hour or kilometers per hour. This is kilometers per second or miles per second. So the speed of light is very fast. It's the fastest thing in the universe. So for black holes, what ends up happening is that you need an escape velocity that's faster than the speed of light to be able to escape from a black hole. And because the speed of light is the fastest that anything can go in the universe, it means that nothing can escape from a black hole, not even light, because you would need to be going faster than that speed in order to be able to escape from it. And nothing in the universe can go faster than the speed of light. So that's sort of what a black hole is. And then we can start to understand what are the different parts of a black hole. So what makes up a black hole? Black holes are kind of simple objects. There's not a lot of fancy things kind of going on in there. They're sort of simple. So at the very center of a black hole is what's called a singularity. And a singularity is where all the mass of the black hole is contained. So all the mass of the black hole is contained in the singularity, and this is an infinitely small point at the center of the black hole. And then black holes also have what's called an event horizon. And this event horizon is the point of no return, basically. So this is the point where you need to be going at the speed of light to be able to escape from the black hole. If you're inside of the event horizon, if you're closer to the singularity than the event horizon, that means that you need to be going faster than the speed of light to be able to escape from the black hole. If you're just outside of the event horizon or beyond the event horizon, you can go a little slower than the speed of light to be able to escape. So stuff outside of the event horizon can escape, but once you're inside the event horizon, you can't return back out. So that's the event horizon. And then next is this Schwarzschild radius. So this is sort of like this funny jargon word. And what this is that it describes how big a black hole essentially is. So it describes the size of the event horizon of a black hole. And the really cool and neat thing about this Schwarzschild radius, the size of this event horizon, the size of the black hole, is that it only depends on how massive the black hole is. So if you have a less massive black hole or a less heavy black hole, the size of the black hole, the Schwarzschild radius, ends up being smaller. The event horizon is smaller. And then if you have a much more massive black hole, if it's heavier, then the size of the Schwarzschild radius ends up being much larger. The event horizon is much larger. So this is the Schwarzschild radius. This is basically how big the event horizon of a black hole is. So those are the few different things that can make up a black hole. And then, so next, the cool thing about a black hole, or maybe it might not be so cool depending on your perspective, is that anything can become a black hole, but you don't have to worry. It's only if you can make whatever thing you want to make into a black hole, if you can make it small enough. So anything can become a black hole if you make it small enough. Even you could become a black hole if you could become small enough. So essentially, what this means is that if you have a certain amount of mass, you can calculate how big the Schwarzschild radius of that amount of mass is. And then if you squeeze all that mass down to that size or smaller, it becomes a black hole. And this is really, really hard to do. So you don't have to worry about this. Somebody won't just come up to you and make you a black hole. So you don't really have to worry about this. So for the Earth, if we wanted to make the Earth into a black hole, the Schwarzschild radius of the Earth's mass is about 1.8 centimeters, or about 0.7 inches across. That's about 3/4 of an inch. So if you wanted to make the Earth into a black hole, you'd have to squeeze the Earth all the way down into that little size of about 1.8 centimeters, or 3/4 of an inch. And that's really hard. So it's almost definitely not going to happen. So you don't have to worry about this. For the sun is much more massive than the Earth, right? So for the sun, you don't have to squeeze it down into as small of a size. because the Schwarzschild radius gets bigger with the mass, so the sun is much more massive. So the Schwarzschild radius of the sun is much more massive. So that means you only have to squeeze the huge sun, the huge entire star down into something that's about 6 kilometers across or about 3.7 miles across. So that's basically like the size of a small town or city. So you have to squeeze the sun down into this really, really tiny size that's basically about the size of a town or city, small city. So, so anything can become a black hole if you can squeeze it down small enough. So that's all well and great. That's like all these different types of things that could be black holes. But what are the types of black holes that we actually know of that live in space? So there's actually mostly, for the most part, there's just two types of black holes that we see in space. Um, so most black holes that we know about in space just fall into these two categories. So one of them is called a stellar mass black hole. These are smaller black holes. And the other kind is called supermassive black holes. That's what we heard about just a few minutes ago when we're talking about the center of the galaxy. So stellar mass black holes are black holes that, as the name implies, are black holes that have masses on the order of stars. So they have masses that are stellar mass. So they're about 5 to about 100 times the mass of the sun. And these particular black holes, we have a pretty good idea of how they form. They form when the biggest, most massive stars go supernova at the end of their lives, and these big, massive stars end up collapsing. The very center, center of these stars end up collapsing, and they form black holes. And because they tend to be formed by stars at the end of their lives, these massive stars at the end of their lives, we expect to find them pretty much where we expect to find stars, especially these big, massive stars. So those are one category of black holes that we know about in space, these stellar mass black holes. The other category is what are known as supermassive. And as the name implies, these black holes are really, really massive. So they have masses somewhere between a few million to a few billion times the mass of the sun. And we actually don't have a perfect understanding of how they're formed. Astronomers, astrophysicists, they have a lot of great ideas of how these supermassive black holes may have formed, but we don't actually have a perfect understanding of how they're formed. And we actually find them in very specific places in our universe. We tend to find them in the centers of most big average-sized galaxies. So they're typically just found in the centers of galaxies, and that's about it. So they're sort of like much more sort of special. These are more rare. They're much, much more massive. So those are the two types of black holes that we know of about in space. So that's basically what black holes are, and those are the types of black holes that we know of. So next, one of the things that we'll talk about in the next part of our show is how we can actually take pictures of black holes. So before I dive into this, I actually want to hear some of your ideas of how we might be able to do this. So how do you think we can take pictures of black holes if they're completely dark? So remember, black holes are so massive that light can't even escape from them. So how do you think we might be able to take picture of a black hole? Because remember, pictures are uh, essentially the light that we see from an object, and we capture that. So that's essentially what pictures are. So how do you think we might be able to take pictures of a black hole if they're completely dark? So I want to hear your ideas. Okay, I'll give you all a few minutes to kind of give your give your wonderful ideas. Yeah, I'm seeing several wonderful ideas. X-rays, you might take a picture with a satellite, maybe use different wavelengths. Great ideas. Scanners, reverse values on the image. Some really great ideas. Look for areas with no stars. Yeah, that's a really good idea. See where you can't see stars behind it. Yep, that's a good idea. Negative filter. Yeah, these are excellent ideas. I really like these. Glow where the light bends around the edge. Wow, yeah. Okay, just maybe a couple more ideas if you have. All right. Yeah, so you all have really, really great ideas of how we might be able to take pictures of black holes or really fantastic ideas. So, right. So this is a really, really tricky problem, right? Like, if you're an astronomer and you want to take a picture of a black hole, that's a really hard challenge, right? Like you can't really take pictures of a black hole because they themselves are just completely dark, right? Like no light can escape from them. So how do you take a picture of them? So black holes are kind of dark, but a convenient thing for astronomers is that some black holes have lots of stuff around them. So there's a few common things that you might actually see around some black holes. So so here's a picture, and this is an artist depiction. This is not a real picture, but this is an artist depiction of a stellar mass black hole. And this is a stellar mass black hole that happens to be living really close to another star. And it's so close to this other star that is the some of the material from the outer envelope of the star, the outer edges of the star, is starting to peel off from this other star, and they're starting to fall in towards where the black hole is. So when that happens, what we expect to happen and what we can see can happen is that this matter doesn't just fall straight onto the black hole. It forms what's called an accretion disk. So as a black hole is trying to eat stuff, it forms this structure called an accretion disk. It's basically this thin sort of circular kind of disk of stuff that's starting to fall onto the black hole or accrete onto the black hole. And black holes are really, really messy eaters. So actually, a lot of the stuff that's falling onto the black hole doesn't actually end up going into the black hole. They're really, really messy eaters. So a lot of it actually ends up going uh, shooting back out of the black hole, and it forms these structures called relativistic jets. So these are jets of stuff and radiation that's shooting out from the black hole as stuff is falling in, and it's just basically it's because black holes are messy eaters, and most of the stuff doesn't actually end up falling inside. So some black holes can have a lot of stuff around them. And then there's another cool property of black holes is that black holes can actually then also bend light around themselves because black holes are so massive, they can bend light around themselves and they can make what are called very unique shadows. So they have a particular pattern in the way they bend light around them, and they end up making these unique shadows. So we can look for the shadow that's cast by a black hole on the light that's coming from its accretion disk in the jet. So this is an animation. This is not actual data, but this is a simulation of what we can expect to be coming from the light being bent around a black hole. So there's a little black hole at the center of this image, and then there's a thin band of light, like sort of maybe like the Milky Way, and it's showing how the light is bending around the black hole as the black hole is kind of moving across this source of light that's behind it. And you can see as it's approaching it, the light is kind of bending around it, and we're seeing it on the other side. When it's over it, it makes this kind of cool looking ring. And then on the other side, we can see the light coming out and bending around it and coming towards us. So if we're trying to take pictures of black holes, even though we're not going to be able to see it, we can actually try to see how it bends the light around it in order to get a picture of it. So it turns out some of the best simulations that astronomers actually have of how light behaves around a massive black hole were actually made in conjunction with the movie Interstellar. So if you've seen the movie Interstellar, you might know that it has a big part of the movie has this huge black hole, and there's a lot of stuff around it. And there are a lot of simulations done in conjunction with the movie by astronomers to get a sense of how does light actually behave around a black hole. So these are some of the pictures from scientific papers that were released in conjunction with the movie to show this. So what they've done in the simulation is that they started out with a disk of stuff. So this might be an accretion disk that's around this black hole. So they just start out with this circular disk of stuff, and then we're looking at it almost from the edge. We're not quite from the edge. We're sort of looking at it from the edge and a little bit above. And then you start out with this disk of stuff, and then you drop a massive black hole at the center of it. And then you see how that ends up bending the light around it. So then they drop this massive black hole, and then this is what you end up getting, you end up seeing for this disk of stuff. So some of the cool things that you can see in here is that the front of the disk, that's not getting bent, like that's kind of still coming at us as it would normally. But then the back of the disk, the part that's sort of behind the black hole, that light is actually bending up around the black hole to come towards us. So it looks like this disk is kind of warped like this. So this is the back of the disk. And then what's even cool and wilder is that we can actually even start to see the bottom of the disk. So remember, without a black hole, we're not actually looking at the bottom of the disk. But if you drop a black hole in there, part of the black hole ends up bending the light from the bottom of the disk, and we can actually start to see that as well. So it can make this kind of cool looking funky shape in sort of the shadow of the black hole. So in the movie, they had a black hole that kind of looked like this, sort of like this. In reality, what astronomers think is it should actually look something like this with a disk that's kind of rotating and a rotating black hole. Is that then you can kind of see that some of the light ends up getting beamed towards us and other light ends up getting beamed away from us. So part of the disk should actually look brighter in reality. In the movie, they ended up choosing this because it looked cooler, but in reality, what we expect to happen around a black hole is something kind of like this. So this is sort of like the shadow pattern that we expect for a black hole. So that's what we might expect if we're trying to take a picture of a black hole. Another challenge is that most black holes are really, really, really tiny on the sky. So that's a really big challenge if we're actually trying to take pictures of them. So if we think back to what stellar mass black holes are, so stellar mass black holes are essentially about the sizes of cities. Like they have event horizons that are essentially the sizes of about cities. So they're, if we're trying to look at, if we're trying to take pictures of those, they're really, really tiny on the sky. On the other hand, one way we can make this problem easier for ourselves is that we can instead try to take pictures of black holes that are really big on our sky. So if we want to do that, we could look at the biggest black holes that we know of in the universe. So these are these supermassive black holes, and those are really huge. So remember, they have event horizons that are really big, that are about the size of the sun to about the size of the solar system, depending on how massive these supermassive black holes are. So if we were trying to take pictures of black holes, we could make our job a whole lot easier if we were to try and do this for the biggest black holes in our sky. So with that in mind, what we can do is that we can think about the two biggest black holes in our sky that we know of. And these are the two biggest black holes that we know of in our sky. One of them is Sagittarius A star. So that's what we talked about in the first part of our presentation tonight. That's a supermassive black hole at the center of the Milky Way Galaxy. And that's a black hole that's as massive as 4 million suns. And that much mass means that it's the size of the event horizon is about 17 suns across. So that's really big. And the distance to the supermassive black hole from us is about 8 kiloparsecs, which translates to about 26,000 light years. So that's basically how far away the center of our galaxy is. It's about 8 kiloparsecs away. It's about 26,000 light years. So that's the supermassive black hole at the center of our galaxy. That's the biggest black hole in our sky. The second biggest black hole in our sky is a supermassive black hole known as Powehi or M87 star. And this is the black hole, the supermassive black hole that's at the center of the M87 galaxy. And this is a galaxy that's located in the Virgo cluster. And this particular supermassive black hole is absolutely giant. It's as massive as 6.5 billion suns. So remember, our black hole is only 4 million suns. And here is this guy, this supermassive black hole that's 6.5 billion suns worth of mass. And that means that it has to be a lot bigger, right? So more massive black holes have to have event horizons that are much bigger. So the event horizon of this particular black hole is about 28,000 suns across. And this particular black hole, because it's located in a different galaxy, it's much further away from us. So this particular black hole is about 17 megaparsecs away from us. So that translates to about 55 million light years away from us. So that's the supermassive black hole at the center of the M87 galaxy. So here's just kind of a picture to help us see these two black holes, just compare them. So again, Sagittarius A star is at the center of our galaxy. So there's our galaxy in our sky. And here what we're seeing are the two Keck telescopes. So these are really big telescopes, and they're looking at the center of our galaxy that's located right there. And this particular black hole is right there at the center of our galaxy for looking at our galaxy from the top. And this is Sagittarius A star. And then Powehi is this black hole that's at the center of this galaxy known as M87. M87 is an elliptical galaxy, though that basically means it's just sort of like a blobby, elliptical blob in there shaped galaxy. So it doesn't have a cool sort of spiral structure like our galaxy. And then if you look all the way, if you zoom all the way to the center of this galaxy, what we see that at the center of the galaxy, right over there, there's a whole bunch of stars, right? Similar to how we have a whole lot of stars in the center of our galaxy. And then also coming from the very center is this huge, really energetic jet that we actually see really well in radio wavelengths. So that's also there at M87. And there at the center of that is this black hole known as Powehi. And the sizes that I'm actually drawing here, these sizes, as I'm showing on the slide, are actually scaled relative to each other to how big they would appear on our sky. So Sagittarius A star, even though it's a physically smaller black hole, it's much closer to us. So that's why it's the biggest black hole that we can see in our sky. It's about 0.02 milliarcseconds across. So milliarcseconds is just a unit that astronomers use to measure how big things are in the sky. And Sagittarius A star is about 0.02 milliarcseconds across, the size of the event horizon of Sagittarius A star. The size of the event horizon of Powehi ends up being a little bit smaller. It's a lot more massive. It's a lot more physically bigger, but it's so much further away that it ends up being a little smaller than Sagittarius A star in our sky. And it's about 0.016 milliarcseconds across. And even though these are the biggest black holes that we know of on our sky, they're actually still pretty tiny. These sizes are still really, really tiny. So to kind of get an intuitive understanding of how tiny these sizes are, you may not have a very intuitive understanding of how tiny this size is. Most astronomers don't either. I don't have a very good understanding of how big a milliarcsecond, let alone a fraction of a milliarcsecond, is on the sky. I don't have a very intuitive understanding of it. So I came up with an example to help us sort of visualize exactly how tiny these sizes are in our sky. So you might know of the moon in our sky. You've probably seen the moon in the night sky. So you know how big the moon is in the night sky, right? And people have landed on the moon. People have walked on the moon. So right here, I'm just highlighting this circle is where Apollo 11 landed on the moon, and that's where astronauts walked on the moon. And this is just a famous picture that you might have seen of a footprint of one of the astronauts on the surface of the moon. So you may be familiar with that, right? So there's the moon, and you know about how big it is in the sky. And let's say next to this footprint, instead of just leaving footprints on the moon, astronauts also left a few quarters on the surface of the moon. So let's just put a few quarters on the surface of the moon. So these are just few quarters coins on the surface of the moon. And it turns out that the sizes of these black holes in our sky, as viewed from the Earth, end up being about the sizes of quarter coins left on the surface of the moon if you're trying to look at them from the surface of the Earth. So essentially, the sizes of these black holes event horizons are about the same size as the sizes of quarters if you're trying to look at them from the Earth that are left on maybe the moon. So the size of Sagittarius A star, the size of the event horizon of Sagittarius A star, is about the same size in our sky as about 1.5 quarters on the moon. And then Powehi is the same size in our sky as about 1.2 quarters on the moon if you're trying to look at that from the Earth. So these are still incredibly small sizes in our sky. These are the biggest black holes that we can see, we could possibly see in our sky, but they're still incredibly small. So this is a really, really tough problem if we're trying to take pictures of them. So we talked about earlier in our presentation that the way astronomers solve these problems, if we wanted to take better pictures of smaller things in the sky, we use bigger telescopes, right? So you might start with some of the biggest telescopes on Earth. So if you're trying to look at wavelengths like optical or infrared, some of the biggest telescopes on Earth are, for example, GTC that's located on the Canary Islands, or the Keck telescopes that are located on Mauna Kea in Hawaii. Or if you're working in even longer wavelengths, like radio wavelengths, you can actually build even bigger telescopes. So the absolute biggest telescopes, individual telescopes that we have on the Earth are Arecibo in Puerto Rico or FAST in China. And these have sizes that are, for Arecibo is about 3,000 meters across, about 1,000 feet across. And FAST, this is a pretty new telescope that's recently been built in China. That's about 500 meters across and about 1,600 feet across. And it turns out even these huge telescopes are not big enough to get sufficient resolution to be able to take pictures of the sizes of black holes in our sky, because these black holes are really, really tiny in our sky. So in order to be able to see these black holes, we actually need an even bigger telescope. It turns out we need a telescope that's about the size of the Earth. And this is where a telescope known as the Event Horizon Telescope comes in. And it's actually not an individual telescope. It's actually a telescope that's built from a bunch of little telescopes that are scattered all across the world. And it uses a technique called interferometry. And this is a technique that astronomers use to get the same resolution as one telescope that's the size of the entire array of telescopes. So in this case, if you have all of these telescopes that are located on different parts of the world, you end up, by using this technique called interferometry, you can essentially get about the same resolution as the biggest distance between any of these individual telescopes. And that ends up being about the size of the Earth. So in this way, astronomers have essentially been able to build a telescope that acts like a telescope that's the size of the Earth. So these are some of the individual telescopes that are located, that make up the Event Horizon Telescope. Here's some pictures of them. So this is the JCMT telescope that's located on Hawaii. This is also located on Mauna Kea in Hawaii. There's the LMT located in Mexico, the South Pole Telescope that's located in Antarctica, and then here's ALMA. This is a bunch of smaller telescopes actually that make up this bigger facility that's located in Chile. So that's ALMA right there. And with this, we finally have a telescope that's big enough to actually be able to take pictures of a black hole. And when astronomers did this, that's what they did. They took pictures of the black hole, Powehi, that's located at M87 star. So this is a picture you might have seen. It made a lot of rounds in the news several months ago when it was first released. This is a picture of Powehi M87 star, the black hole at the center of the M87 galaxy, as taken by the Event Horizon Telescope. So this is a really pretty picture and it's really cool. But what's kind of interesting is what's also interesting is some of the science that you can also already start to see from this picture. So what we're seeing in this picture is light that's coming from an accretion disk that's sitting around the black hole. So what we're essentially seeing is light that's coming from an accretion disk, as we were seeing in those simulations from before, that's bending around the black hole from its unique shadow pattern, and also the light from jet structure, possibly. So, so here are some scientific figures from some of the science papers that came around this image release from the Event Horizon Telescope collaboration. So this is the picture of the black hole taken on one of the particular nights that went into the observations. And here, right here, these are some of our best simulations of how matter behaves around close to a supermassive black hole, like the one in the center of M87. These are GRMHD simulations, standing for General Relativistic Magnetohydrodynamics. So these are some of the best models of how we expect that matter behaves close to a black hole. And this is one of those models. And using this model, what these scientists did was that they used one of these really good models and they blurred the image similar to what was observed. And what they ended up seeing is that their models are pretty close to what we're actually seeing for this particular black hole. It's not quite exactly right, exact, but it's very close. So these models, what that tells us is our expectations of how matter behaves close to a black hole by some of our best models to simulate that are actually pretty good. So that's really interesting. This is another figure that's kind of lets us understand how the jet and how the jet in M87 might be pointed, and how the disk of stuff that's accreting around the black hole, that's rotating around the black hole, which direction it's rotating relative to us. And it's showing the different possibilities of how the jet is pointed versus how the disk is rotating and how that could affect the final image that we're getting out of it. And this is just some more simulations of how the light from a jet, depending on the orientation, how the light from that jet can get warped by the black hole's shadow pattern. So these are all some of the cool science that astronomers have been able to get from this really pretty picture. And another of the really neat things that they noticed was, so it turns out the observations that went into making this final picture, these observations were actually conducted over 4 different nights in April 2017. So they took observations over 4 different nights, and then they combined them together to make the final image that was released. So here is another figure from one of their papers. And here what they're seeing is like, this is just kind of seeing the individual images from different nights that the observations were conducted. And this is not something that's very strongly detected, but they're able to see some signs that there's actually changes in where the bright spot in the accretion disk is moving. So what that suggests to astronomers, what that suggests to us is that what we might be seeing here is movement in the accretion disk from day to day. So we might be seeing changes from day to day. So that's happening. That's something that we can see on the level of different days in these observations. So that's super interesting. So that's Powehi, the black hole in M87. And you might be saying, by seeing this pretty image, it's a really cool image, but you might be saying, well, Poehi is super cool and all, but what about our galaxy's black hole? What about Sagittarius A star? And it turns out the Event Horizon Telescope actually hasn't yet released a picture of Sagittarius A star. So we don't actually, maybe some of the folks working on it know what it looks like, but the wider world doesn't yet know what Sagittarius A star looks like yet. We don't have a picture of it yet. Um, and there's a couple of reasons for this. So intuitively, what you might expect, well, Sagittarius A star is the biggest black hole in our sky. So it should maybe be the easiest, right? Easiest to take pictures of. But it turns out that Sagittarius A star, that the black hole at the center of our galaxy, is physically much, much smaller than the black hole at the center of M87, Poehi. So Sagittarius A star is only about 17 suns across, whereas Poehi is much more massive and it's about 28,000 suns across. And essentially what that means is that stuff can move much faster around Sagittarius A star than it can move around Poehi, because Poehi is the size of Poehi is much more physically bigger. So essentially, the way this technique kind of works, you can kind of think of it as this analogy that these astronomers are essentially trying to take a long exposure photo. And Poehi is this great subject that's like sitting nice and still for us to be able to take a picture of it. Whereas Sagittarius A star is maybe like a hyper dog that you might have that's like constantly moving and you're trying to take a picture of it, but it's just constantly moving. So you can't take a good picture of it. It's just always sort of like looks like a blur. So that's why this is essentially, that's a way to kind of understand why this is trickier. So the astronomers at the Event Horizon Telescope collaboration are working really hard at this. So they have some techniques that can help them still take an image of this black hole. Uh, so, so I'd encourage you to stay tuned for more news that might be coming from this from the Event Horizon Telescope collaboration in the future, and we might all get to see what the black hole at the center of our galaxy looks like, what Sagittarius A star looks like. Um, so that's how you can take a picture of a black hole, and that's what a picture of a black hole looks like. So that's about the end of my show. But before I sort of wrap up, I just want to kind of emphasize how all the really cool science that I've been showing here, this is science that's done by a whole lot of astronomers. It's really amazing work, and it's made possible by huge teams of astronomers that work on this. So, for example, some of the science that I was showing in the first half of my talk, but studying the center of the galaxy, that's something that astronomers have been studying worldwide. Have been studying the center of our galaxy for over 50 years, and they've been studying the stars orbiting around Sagittarius A star, this supermassive black hole at the center of our galaxy, for over 25 years. So this has taken a lot of work for a lot of astronomers all across the world. There's a lot of us here at UCLA who work on this as part of the UCLA Galactic Center group, and there's also a whole lot of astronomers all across the world that also work on this. And the black hole image that you may have seen, that black hole image is also really cool. And I think it's really neat that it's built from a huge collaboration of over 200 astronomers located all over the world. And just to get that one image, that really pretty image that we saw, that's taken hard work for over a decade to be able to get that really, really pretty image and to be able to build a telescope to be able to get this really, really pretty image of an object that's just so, so tiny in our sky. So, so that's essentially the end of my show. Before I completely close everything off, I can take a few more questions that folks might have. So I see like throughout the show, you all have been posting some really great questions in the chat. So I can maybe kind of answer a few of them. So, so one of the questions is where is Earth in the Milky Way? So that's a great question. So um, remember when we were looking at this picture of the Milky Way, right? Near the beginning of our show, we saw this is sort of like a map of the Milky Way, and these are all sort of like the spiral arms in our Milky Way. Um, uh, so right here in this map where we see it's labeled the sun, the Earth orbits really close to the sun. So the Earth is basically right where the sun is in this picture. The solar system is really, really tiny compared to the size of the galaxy. So we're right over there where the sun is, located on Earth. So the Earth is right there, exactly where the sun is. So that's a great question. Another question is, how do we know that there are spiral arms? If I was a chocolate chip in a pancake, I wouldn't know if the pancake was round or Mickey Mouse shaped, right? So that's a really great question, and that's a really great thing that you picked up on. So fortunately for us, we're a little smarter than chocolate chips. So astronomers have a lot of very clever techniques to be able to understand how our pancake looks. So, for example, something that astronomers can do is they can sort of map out different parts of the galaxy and kind of see how fast they're moving. They can measure how fast they're moving relative to us, and then that can actually tell us where they're located in the galaxy. And they can use that and some math to kind of make up a map of the galaxy. And this is sort of like a detail that I kind of brushed over, but this being able to tell that we're located in a spiral galaxy and being able to even map where the spiral arms are has taken a lot of hard work. So yeah, that's a great point that you noticed. And fortunately for us, we're just a little smarter than chocolate chips. Um, so another question is, why are the photos of the center of the galaxy so red? Uh, so that's a really fantastic question. So it actually turns out, like for example, maybe these photos that we were looking at, or maybe even these photos that we're looking at, um, these photos are actually in near infrared, so they don't technically have a color that our eyes see at. Um, and they're taken with a near infrared filter. So what the telescope is basically recording, it's taking a picture and it's just seeing how bright this part of the sky is versus this part of the sky, how bright this part of the sky. So it actually technically doesn't have a color. We can put a color sort of on top of it afterwards to help our eyes kind of see what's happening. But as the telescope gets the image, the color of this light is technically just near infrared. These particular images happen to be have wavelengths of around 2 microns. It's not a color that our eyes can see at, but a telescope can see that, and these special instruments can see that. And we've just kind of colored them red to kind of help us see what's happening. But the images that come straight from the telescope don't have an inherent color. And that's a great question. Um, why don't those stars near the black hole get sucked into it? That's another great question. And uh, this is something that I feel that black holes actually get a really bad rap. Um, they're not these evil sucking things that are in the universe that are just sitting there, just sucking in everything. Um, uh, and it turns out black holes, things can kind of go into a black hole only if they're sort of like really close to it. So uh, further away from this, like it just kind of acts like just a point of mass that just happens to be a certain mass, and things around it just kind of behave as they normally would if there was just any other object with that much mass that was just sitting here. Being a black hole doesn't make it any different. Another way that helps me kind of think about this sort of more intuitively is that let's say all of a sudden one day the sun turned it into a black hole. Um, if that were to happen, for us sitting on the Earth would just keep on happily just orbiting around the sun because it just still sees that there's that much mass at the center. And that's all the Earth's orbit really cares about is that, oh, there's this much mass inside my orbit. So it'll just keep on happily orbiting around where the sun used to be if it just suddenly turned into a black hole with the same mass. So that's a great question. It would lead to a lot of other problems. For example, the sun isn't just a source of mass, it also provides a lot of light and everything. But in terms of the Earth's orbit, we wouldn't notice. The Earth would just keep on happily orbiting around um, this new sun mass black hole, just as it was before. So that's a great question. Um, So if a star becomes a black hole, the gravity doesn't change, right? Just the volume it occupies is reduced. So it doesn't suddenly start sucking things around, right? Yeah, so that's exactly right. So you're exactly right. So this is essentially what I was just talking about just now. So yeah, if a star were to become a black hole, the gravity doesn't end up changing. It just sort of depends on the mass of the star. So yeah. Um, so what discovery most impacted you? Um, well, that's kind of hard to say. Uh, like, I personally work on galactic center science, and that has always been very inspirational to me ever since I first learned about it when I was a college student. I first learned about the center of the galaxy then, and that always just really fascinated me. And then I think, like a lot of astronomers, when this first image of Boehi came out, uh, the black hole that's at the center of the M87 galaxy, that was really moving because, right, I mean, it just kind of looks like a blobby donut, but just if you sort of like know what it is, that this is the first time we're kind of able to get a real good picture of close to a black hole, the disk around a black hole. It was very impactful, and also just from the perspective of like it kind of looks like a blurry donut, but this is the sharpest image that we've sort of like taken ever, that anything's ever taken. Remember, this black hole is incredibly tiny in our sky. So this is uh, uh, the sharpest image, at least so far, that's been released, that's been ever taken by humans. So that's also just a really, really cool fact about this. So I would say that was also a very impactful thing. Um, maybe one more or so. Um, are the Keck telescopes affiliated with JPL? So the Keck telescopes, so this is they're operated by a big collaboration of astronomers. They're largely operated by a collaboration of astronomers at part of the University of California system and uh, Caltech, which is California Institute of Technology. There's also several other astronomers across the world at different institutions that also contribute to it. So, for example, yeah, astronomers at NASA as well. So in that way, it is somewhat affiliated with JPL, but not directly. Um, yeah, so I think these are some really, really great questions. Yeah, so I'll start to wrap things up now. Thank you all for coming to our show. And just I'll kind of switch over to Stellarium really quick. Just before I kind of wrap things up completely and close things out, I really encourage you to try and go stargazing, try and find a dark location away from the city lights if you can, and try to go stargazing if you can. And you still have a few more weeks before you won't be able to see the center of the galaxy in the night sky anymore. So the center of the galaxy is something that's up in the night sky sort of during the summer months. You can first start to see it later in spring, maybe around like March-ish, maybe even late February if you were very patient and waiting up until the early morning. And then you stop being able to see it later in the summer, basically around nowish. So I really encourage you all to try and catch the center of the galaxy. You still have a few more moments this year. And try and find the center of the galaxy yourself. Try and find Sagittarius and look for the center of the galaxy. Jupiter and Saturn are pretty close by too. So if you have a pair of binoculars or maybe even a telescope, then those are also always good targets. So yeah, thank you all for coming to the show and hope you all enjoyed it. And thanks for all the great questions and comments throughout the show.